Okay guys, let's see if I can finally do today's video right. This is like version 4 of this video. It's ridiculous. I wanted to sit outside, but the guy across the street from me is getting a pool put in, and that was too loud. Then my garbage can blew away in the wind and I had to run and go get that. And then my battery died. So now I'm inside the house, down in my basement, ready to go. So back to the work. At the top of the sheets today, you got the same diagram as before, except I had already started labeling it. I wanted to remind you that there are 3 stages to this whole photoelectric effect idea. Number 1, you've got light energy coming in, and that energy has one of 2 formulas, either E equals HF or E equals HC divided by wavelength. Both the same thing, just 2 different ways of doing it. And then in step number 2, the light hits a metal and there's an interaction with the metal. And in step number 3, electrons are ejected from the metallic surface. And at that point, they're not light particles anymore at all. So actually, that's important. The red marks on here, these are photons, particles of light. Photons come in, electrons go out. 2 totally different particles. And the bridge between the 2 is this metallic surface that vibrates under the energy of the incoming light. So today we're going to be looking at this vibration itself. I want you to think of it as like this is an energy conservation situation. And remember what I was saying about energy conservation. When you understand how to do any energy conservation questions, you can do any energy conservation questions. The only thing that's going to change is the formula or the individual formulas. When the metal itself is bathed in light, the metal, depending on what the metal is made out of and the atomic structure of that type of metal, there will be a vibrational sort of absorption of some of the energy due to, it's almost like friction. I mean, think about it as friction, but it's like internal friction. The metal itself can sort of shake and shimmy and vibrate at an atomic level and absorb some of the energy of the incoming light as, well, it might not be heat exactly, but think of it as heat. The metal itself will absorb some of the energy as internal heat, which is kind of the same as friction, and basically what I'm getting at is it's work. So some of the incoming light energy is going to get converted into work energy, but this work is not a movement from point A to point B, it's the actual metal itself sort of shaking. And that's why the title of today's work is not just the word work, it's called work function. So it's the word function is tacked onto the end just to kind of differentiate it a little bit from what you normally think of as work, because there isn't actually an object moving in this question, scraping along a surface like work we've done in grade 11 and in the first part of grade 12. So each metal has the ability to convert some of this light energy into work. And every single metal is different. So there's 2 things on this sheet that I want to call to your attention. One is a definition for work function. Please read through this. But basically it's what I was describing. Each metal has the ability to sort of absorb some of this light energy. And then in the bottom corner here is a chart of all the different work functions for several different metals. And this chart, of course, would be thousands and thousands of metals long. This is just a clip out of the textbook featuring some of the common metals that are used and their work function. Now, the only tricky thing that you got to get used to right in the beginning is work function is always given in electron volts. It's a sort of a strange industry standard, and electron volts is a suitable unit to be used for energy. However, it's not the standard metric unit that we use. So you're going to have to get over this. You're going to have to, even though everything's given in electron volts, you have to use it in joules. And that means that you unfortunately have to convert these work functions into joules in order to use them. And the conversion is right here. That 1 electron volt equals 1.6 times 10 to the negative 19 joules. This is one of the reasons actually that electron volt was started as a unit, because the exponent negative 19 is also the charge on an electron, for those of you in chemistry class. So a new sort of unit was created just for this work based on how many divisions of electron charges are involved in this energy. I don't know how else to say it. It's kind of confusing, but it's very easy once you start doing questions. Big empty space here on the left. I don't really know what we can put in there, I guess. Well, you know what? Why don't we put this in there at least? And I don't want you to memorize this because, again, there is no memorization to any of this. But if you have a metal and light energy comes in, that means you're starting with this. You're starting with photon energy and nothing else. You strike the metal, some of that energy gets transferred into the vibrational energy in the metal itself. That's called work function. The symbol for work function, for some reason, is a italicized. It looks like an italicized capital W. It's actually not a capital W. It's a Greek symbol. I forget what it actually is. And they often write it with a little 0 after the end. I don't know why. That's just the standard. And then electrons are going to get shot off. And this is energy of electrons. So think about the conservation of energy formula that would match that. Because again, when you're doing conservation of energy, you don't need to be told what the formula is. All of the energy in the beginning has to equal all of the energy in the end. But it's going to split into two different forms. So basically, we have a situation like this. You've got photon energy is the total energy in the beginning. It has to equal the sum of all the energies in the end, which would be work function and the energy eventually of the ejected electrons. And the important thing here is to realize that, again, even though you sort of think of work function energy being taken out of the situation, there are no negative signs. Think of it as it splits into two forms. And if you were to add these two together, you'd get the same energy as before. Well, this sort of expression right here, and I put a box around it, but I wouldn't suggest putting a box around it because I don't want you to memorize it, but that is basically what you need for all of this work. That's the conservation of energy formula that matches everything. And then the question is, how many different ways can you think of, how many different versions of questions can you ask where you attack this formula from all different sort of angles or directions in the formula? Let me show you what I mean. Here are some typical examples, and I'll show you how easy this work is. So question 1, calculate the energy of ejected electrons. So that's the end of the situation. If a piece of iron is bathed in electromagnetic radiation of frequency this. So there's two givens in this question. They give you the frequency of the photons and the material that's being used in this question, which is iron. So first things first, look up iron on the chart. It's got a work function of 4.67 electron volts. So let me write that down. 4.67 electron volts is the work function in this question. So you could do this in one giant formula, which actually is the preference. It's a conservation of energy question. But let me attack this one in little parts just to show you how you would do it in little steps. First of all, you could calculate the energy of the incoming photons. You have two different versions for that energy. Frequency is given, so let's use the short formula. Energy is going to be HF. Your H is 6.63 times 10 to the negative 34 joule seconds. Remember, that's a constant. And the frequency in this question, 1.13 times 10 to the 15 hertz. So this will give you the energy in the beginning coming in. And really, that's going to be the total energy anywhere in the entire question. But okay, so we've got 7.49 times 10 to the negative 19 joules. So some of that energy is going to get absorbed as work function in the actual iron itself. Iron is capable of absorbing 4.67 electron volts of energy. And again, there's a unit conflict here. This is electron volts, this is joules. I mean, really, we're just going to take that off of this, but the units don't match. So what you have to do in the beginning, going back, is you have to remember to convert electron volts into joules. The conversion factor is on the front of this page. 4.67 multiplied by 1.6 to the exponent negative 19. 7.47 times 10 to the negative 19 joules will be absorbed in this situation. So think of the theory here. 7.49 is falling on the metal, 7.47 is going to get absorbed, and there's going to be 0.02 left. But again, I don't like the way this is written out. I was going to subtract the two and get an answer, but really, what formula are you going to use at that point? The real way of doing this, I'm going to leave those numbers up there just for reference, but let's do it like this instead, because really, this is the point. Conservation of energy. All the energy before equals all the energy after. Work function and photon energy. Okay, so we know that the energy in the beginning is 7.49 times 10 to the negative 19. The work function has been worked out as 7.47 times 10 to the negative 19 joules this time. And we are looking for photon energy in the end. Oh, sorry, this is important. I made a mistake here. On the right-hand side of the formula, we're not dealing with photons anymore. These are electrons. And exactly what the question's asking. What is the energy of the ejected electrons? So this is a very simple rearrangement. And just to make sure that I'm going to get my decimals right here, I know this is kind of silly. I mean, I can see what the answer is going to be looking at that right now, but I don't want to make any mistakes on the video here. And the decimal is going to shift when it gets expressed properly in scientific notation. It comes out to 2 times 10 to the negative 21 joules. Energy of the ejected electrons. Okay, example 2. Let's try one more. Uh-oh, this question doesn't have any numbers in it. What the heck are we going to do? So, let me read it. Calculate the wavelength of electromagnetic radiation that will have just enough energy to cause photoelectric effect on a surface made of cesium. So in actuality, there are two givens provided in this question by the words. The metal is cesium, so right away you know that you can get the work function. And this word just is very important. Just enough energy to cause photoelectric effect. Just enough energy. What the heck does that mean? Because remember what I was saying earlier in this course. The word just is like the word rest in grade 11. It always means something. And that's why I italicized it. Here's our situation. You've got photon energy coming in. The metal itself absorbs energy due to its work function. And then if you overcome the work function, and I almost wrote the word photon again. If you overcome the work function, the energy that's left over will eject electrons with building amounts of energy depending on how much energy was used in the beginning. Well, this word just, what that means is how much energy are the ejected electrons going to have? If they have just enough, 0.1 joules, 0.00000 joules, 0.0000000, I mean, how many zeros? We're just going to make it 0. If it has just enough energy, think of it like this. The energy of the incoming photons was just enough to absorb what the metal itself could handle, and now any energy that's left over is going to fire electrons off. Okay, and then just like any other energy question in grade 11, once you have your energy expression, you fill in your givens. You look up formulas. Work function doesn't have a formula. It's right off the sheet, but photon energy does. There are two different formulas, and this question's asking for a wavelength. So this time we're going to use this formula. hc divided by wavelength is going to equal the work function. And I guess the question is, what is the work function of cesium? So flip back to your chart. Cesium 1.95, but again, use the conversion factor. So 1.95 has to be multiplied by 1.6 to the exponent negative 19 before you can use it. 3.12 times 10 to the negative 19 joules. Okay, so the incoming energy has to match that exactly, and then the theory would be any tiny little bit more energy on the left-hand side would be left over for the ejection of electrons. But we're going to figure out what the absolute minimum is here. So we are looking for a wavelength. Rearrange this formula. hc divided by the work function, 3.12 times 10 to the negative 19. Sub in your constants. 6.63 times 10 to the negative 34 joule seconds. C is the speed of light. 3 times 10 to the 8 meters per second. Also the speed of all electromagnetic radiation. Doesn't just have to be visible light. And you're looking at a calculation only. 3 to the exponent 8 divided by 3.12 to the exponent negative 19. Okay, gives you an answer of 6.375 times 10 to the negative 7 meters as a final answer to that question. And you could actually match that up to a color of light if that fits into the color range. I think it does. I forget where visible light ends. That's 638 nanometers, which you could look on the chart and see what color that is, unless it's off the end of the range. Okay, well, there are 3 questions that you have to do for practice today, but don't think of these as practice questions. Think of them as 3 more examples. Example 3, example 4, example 5, even though they're numbered 1, 2, 3. See if you can get answers to these questions. It's really important. We're at the end of the course now. We've got just a little bit of work left. As soon as we take these questions up, we are going to have the first assessment for the quantum work, and then we're going to do a couple of lessons of quantum next week and end it off with one final assessment. So I will post answers to these in maybe later tonight, possibly tomorrow morning, and definitely try these questions out. Don't wait for the solutions, because you have to know whether you can do these right. And this time I don't have answers on the sheet, so you're not going to be able to check yourself. This time I did it on purpose. I want you to get your best answer and keep all your decimals, and let's see if your answers match up to what the real solutions are.